Good morning, everyone. This is Jim Chastain with EasyPower, and today we have guest speakers from the Eaton Corporation and a fairly exciting technology presentation for us all. Before we start, I'd like to run our poll questions. If you would please help us participate with your feedback. Certainly there's no obligation or liability. The first question is, what is your preferred method for reducing the risk of arc flash around low voltage equipment? You can indicate by checking your desired methodology. Here's how folks weighed in. Interesting. Now the next question is, if you use specific arc flash if you don't use specific equipment, why not? What's your position in terms of taking that next step? And here how folks have weighed in on this one, which is not surprising in today's day and age. And then the final question, what incident energy level do you try to target in your overall corporate policy? All right, let's see how folks weighed in on this. All right. And so with that, I'd like to turn the conversation over to Mr. Chris Connors, Applications Engineer with the Eaton Corporation. Chris, it's all yours.
Thank you. Again, it's Christopher Connors, Eaton Corporation. I am the Applications Engineer sitting in Morrisville, North Carolina. I have some ties to the low voltage switchgear product line that's based over in Asheville, North Carolina, where we manufacture our low voltage switchgear equipment. Later in the presentation, Adams Baker, the product manager for that product line, will actually step in and take over the remainder of the conversation once we talk about the product. On the front end, what I'd like to do is discuss what the current state of arc flash is and what that problem and how that presents itself. So when we discuss arc flash, since NFPA 70E was released in 2002, the conversation has grown, the engineering controls have gotten better, the technological solutions that have been presented by equipment manufacturers such as Eaton has increased in number and type and definition, but all of those are trying to fix one problem: reduce the incident energy as low as technologically possible to do many things. Obviously improve the safety around the equipment while it's operating, and then of course to protect the equipment and minimize process downtime or losses to the system. Prior to the 70E release in 2002, there wasn't a empirical method to calculate what the hazard was. Everybody knew that arc flash events were possible. Everybody knew that there were hazards associated with working around live equipment, but there wasn't really an effective way to quantify that. So IEEE and NFPA worked together, came up with some methods to calculate what that incident energy was, and that's how software such as EasyPower and other calculation methods come up with an incident energy that is then used to produce some level of PPE or protection rating that we need to follow to operate around the equipment safely. So that incident energy really only has three major points that go into the calculation: the available fault current, which is typically an upstream transformer source that's close to the equipment, or if it's a downstream branch piece of equipment, it's whatever the available fault current minus the cable impedance is coming down the wire, so to speak, to that equipment. The distance that the person is from the point of the arc or from the front plane of the equipment, and then the clearing time on the OCPD device, whether that's a fuse or a breaker. Typically, clearing that fault relies on opening an upstream breaker. Fuses get used in a lot of systems nowadays but their favor fallen out, decades ago. So most people design around circuit breakers due to the ease of resettability and service once they've been installed. When we're discussing the clearing time on a circuit breaker, there's two pieces that go into that. And those two pieces are the detection time for whichever the trip unit is that's inside the circuit breaker, and then the mechanical time that the circuit breaker actually takes to open a set of contacts, draw an arc through a set of arc chutes, chop that arc up in the ionized gas, and actually clear the fault and stop the fault current. So that clearing time, combined with the other two elements, is how the incident energy gets calculated. The current rules with NFPA 70E dictate that incident energy shows up on an arc flash hazard and safety label, and that's what we're showing on this slide. So in the example that's here, there's a 4.1 calorie incident energy at a 1 foot 6 inch or an 18-inch working distance. That working distance is very common because that's basically your arm's length from the front of a human torso to a hand where you're operating a breaker toggle or a push button on a circuit breaker. So how do we get to reducing that incident energy? Well, there's a lot of different methods to detect the fault current as it starts flowing through a circuit breaker. And nowadays, most of the technology has gotten to the point where they react in less than one cycle, many in a matter of milliseconds. There are, analog circuitry such as Eaton's patented ARMS technology, electronic means via standard trip units, and then, there exists, fusing and other things that are, also able to act very quickly. Low voltage power circuit breakers, per UL standards, can take up to 4 cycles to physically clear a fault after it receives a trip signal. So in the terms of an electrical arc fault, that's kind of an eternity, right? So if I have a trip unit that basically reacts in 0 time, I still may have to wait up to 4 physical cycles for the mechanism of the breaker to physically open. So that's a physical limitation of the mechanical systems that are built into the circuit breaker. No matter how fast I can detect that fault, regardless of what method I'm using to detect it, there's going to be a delay and no further way to achieve a reduction in incident energy because I can't make the breaker physically faster. So if I'm looking at the NEC and I'm looking at my 240.87 rules, they give me a lot of different methods by which I can use to mitigate arc flash energy and zone selective interlocking, diff relaying, energy reducing maintenance switches, arc detection relays, light detection systems, even adjusting the instantaneous now on circuit breakers with the new 2017 NEC are all available as methods. They have differing abilities to limit how much fault current, but they all rely on a circuit breaker that can't go any faster. So if we had a solution that could hasten the response and work around the limitation of a circuit breaker's mechanism to speed up the reaction, then maybe we can further reduce the incident energy. Another method, or a method for that, it does exist in the market. There are a couple manufacturers that in the industry create they build bolted fault, or what we call in industry crowbar devices that do arc mitigation. That can react very quickly, much faster than a low voltage power circuit breaker. By doing so, they react fast enough to change the mathematical equations in favor of a reduction in incident energy by basically fault closing on the line. So that way the arc fault incident energy doesn't flow downstream to the point of the arcing. It actually creates a bolted fault current through the upstream portion of the system. But that comes with consequences and limitations as well. If we do a bolted fault above the arc fault, there's a lot of maximum peak fault current would be drawn either through the secondary of a transformer or provided downstream from all the upstream sources. So what that can do if things aren't properly braced and properly secured in the terms of like cables that are terminated in the back of switchgear cabinets or breakers, or in the case of bus bar that's in switchgear, or bus bars that exist in like big power transformers, those things can all deflect and move. For those that have ever seen a a video of like a cable faulted that's unrestrained. Those tend to whip under the forces of the electromagnetism. And that actually happens on a large scale inside the switchgear if you decide to fault it. So transformers get stressed, cables get stressed, bus bars can bend. There's a lot of things that can happen because it's basically an unrestrained voltage fault. So it's not ideal to stress a power system in that manner, and can only handle it so many times before something will give. So maybe there's a method then to current limit that type of action. So a solution could be to use that type of method, but put a device in there that has some sort of current limitation to not draw the maximum peak fault current like a voltage fault device, but still provide the reaction time and still draw the arc energy away from where the point of the fault would occur, thereby protecting the equipment and reducing the damage that would happen on that equipment. So other methods that are out there, which, via the polls, it seems that a lot of you are already specifying, arc resistant switchgear by producing equipment that has heavier duty enclosures, has baffling, has channeling, has plenums. We can take the instant energy if a fault does occur and push it out in a direction that's away from the user. The current standards that are out there for most of the major manufacturers are it's the ANSI ratings type 2B, and it's able to basically protect the entire perimeter of the switchgear plus any instrumentation compartments that get opened. This type of gear comes at a little bit of a footprint cost from an overhead perspective. You usually have overhead clearances that need to be satisfied, like no overhead conduits, cables, wires, light fixtures, those sorts of things for some distance. Or if you're going to do a plenum vent, that now needs to get ducted out somewhere, usually to an outside room or an outside, external to the environment. Then that space needs to be saved off, typically with fencing or something to prevent any injuries. If an arc flash does occur, that energy blowing out a side vent, on the side of a building won't injure somebody out there. So there's a lot of design considerations that need to be made with equipment like this. You also generally can't configure the equipment the same way you would configure traditional switchgear. So there's some limitations in things like breaker placement and how you can arrange the components within the gear to satisfy the lineup. So those things come at limitations. With arc resistant switchgear, there are other things that do limit you. When you open a type 2B metering compartment or control compartment, you're safed off. Those compartments are labeled and able to be accessed while the equipment is live without having to carry or wear the PPE required to protect you from an arc flash around that equipment. But let's say you have to fully rack out and withdraw a breaker. That may be due to needing to replace a trip unit, add a shunt trip, add an aux switch, move a key interlock. There may be many reasons why that breaker needs to be removed. Maybe you're doing routine maintenance and that maintenance requires the breakers be removed for primary injection, but the owner wants to continue operating the switchgear. Well, the minute that bolted and latched compartment door is opened for that breaker, now that equipment is not arc resistant anymore. And whoever's operating in front of the gear needs to be wearing appropriate PPE for the arc levels that are present if we consider the gear to be non-arc. If I walk around to the back of the switchgear and let's say I want to do infrared scanning for maintenance, or I need to do some sort of checks in the back of the gear, it's the same scenario applies. The minute those doors or compartments are open, the arc resistance is compromised in the equipment, and now it needs to be considered non-arc, and thus your clients would need to be, or you as a customer would need to be wearing the appropriate arc flash PPE. There are other methods out there from a technological standpoint that over the last decade have gained a lot of traction with the discussion about reducing arc incident energy, and that arc detection relays and relays that also receive arc optical inputs have come to the forefront. I can name a couple different manufacturers that have been in the market for quite a long time. Eaton has been doing these for a few years, but there's certain limitations that come with doing light detection as well. The light detection system, while everyone is of the understanding that light detection is faster than a direct electrical method of measurement and then, you know, circling back to a circuit breaker to operate it. What cannot be expressed empirically is what the actual clearing time changes by utilizing these methods. And that has to do with tested combinations of equipment. That has to do with light detection sensors being in non-repeatable places within equipment, and the fact that equipment varies from design to design as they're implemented in the field. There's also some design limitations that come with by using light and combining it in a power circuit breaker scenario. When a power circuit breaker operates to actually interrupt a normal fault, it will actually puff some light and smoke into a circuit breaker cubicle just by action of doing its normal job. It could be just a standard overcurrent situation or a normal kind of fault interruption that's not an arc flash. And so then if you have a light detection method in that cell, now you need to start iterating to sensitivity that's going to be appropriate for that breaker in that situation. So you may need to desensitize the light detection to accommodate for the breaker's physical normal operation, and thereby not really getting the level of arc resistance or incident energy resistance that's desired. The other thing that's kind of an unsaid is when you're using a light detection system, because it can't be empirically linked to the actual reduction in time by most accounts, none of the manufacturers, by applying these types of systems, can give you a direct number by which to change your model. So when you are modeling the system for clearing time, you still have to rely on the actual circuit breaker to make sure that your clearing time is accurate. The arc detection system, including Eaton's, is not by itself able to claim the actual reaction time to quench or to stop the arc. So what would be the ideal arc flash mitigation system, given that we've kind of discussed a bunch of different technologies that are out there and methods that exist today to be able to counter the incident energy? Well, a system that acts faster than a low voltage power circuit breakers for cycles, or some manufacturers come into 3 cycles, would be ideal. You would want a system that, unlike a bolted fault, draws less peak fault current to protect your upstream cable, your upstream transformer windings, any sort of things that may potentially be improperly installed that could cause a secondary arc fault if something were to come loose, like a poor termination on a cable. You would want something to reduce or eliminate arc flash damage to the switch gear. If I can operate so fast that my incident energy is negligible, well, then maybe the physical damage to the equipment could be negligible as well. And then once I've removed the source of the fault, I can go right back to operating. I know for a lot of data center folks, hospital folks, process folks, that would be something that would be ideal, right? If I could be back up and running in 20 or 30 minutes or an hour, that's a lot better than an arc flash that then destroys a piece of gear and takes weeks to get replaced, or usually months. It would be great to achieve arc flash ratings, get that ANSI C37.20.7 rating without the traditional arc construction techniques and without the limitations about doors. It would be nice to be able to say IR scan a piece of gear without having to wear all the heavy PPE. It would also be nice to not nuisance operate, to not have to worry about desensitizing any of my equipment, to just navigate around the traditional methods that the traditional systems that are in the gear and going to be present anyway. And then lastly, all of the systems that have some sort of detection method to date have administrative controls. You are forced to turn on an emergency or a arc energy reduction mode. You need to turn on a maintenance mode. Somebody needs to write an MOP to know when I'm working on, piece of downstream gear X or a motor control center Y, that I need to go upstream to a particular breaker and turn on or, somehow enable whatever the system is. It'd be a lot nicer for the customers and clients to be able to walk in and know that the equipment is already protected. So from a consultant standpoint, it'd be like spec it and forget it. If it shows up and it's there, it's always working and it's always protecting the customer. My background with Eaton was about a decade's worth of actual field service. So I used to be one of those folks that had to go into systems that were most times dead, but sometimes you had to work on live systems and do some sort of maintenance or do some sort of operation that required operating around live equipment. And I can say that most customers, when I would visit them, wouldn't necessarily be aware of all the things that they needed to do to safe out their equipment properly, because it's not a thing that an activity that they do on a regular basis. So something that's passive and always operating in the background to protect would be ideal. So with that, I'm going to turn the rest of the presentation over to Adams Baker to introduce our Arc Quenching Switchgear, which would then answer all of the questions that we had on the previous slide. So with that, I'm going to give this over to Adams.
All right, thanks a lot, Chris. I appreciate it. As Chris said, my name is Adams Baker. I'm the product manager for Eaton's low voltage switchgear out of Asheville, North Carolina. That's where we engineer and manufacture all of our low voltage switchgear. So Chris, I assume you can see my screen?
Yes.
Great. So Chris did a great job of highlighting a lot of the options that are available to us to reduce the risk of arc flash, whether it be just to protect the equipment or obviously mostly to protect personnel that are working around it. He also highlighted some sort of opportunities for improvement, if you will, that a lot of these systems, room for improvement that these systems have. So Eaton acknowledged these shortcomings, if you will, in a lot of the existing technology. And with those shortcomings in mind, those shortcomings that Chris highlighted in sort of that ideal system, we went back to the drawing board, and what we did is we developed a technology that really tried to ameliorate all of these shortcomings of arc resistant, arc detection, energy reducing maintenance, which is ZSI, using a breaker to clear the system, et cetera. That would address all those shortcomings in a singular product that would really make equipment safer to be around. So what our engineers came up with is what we call Arc Quenching Switchgear. It's an active system that enhances safety, it protects uptime, and it protects the switchgear in the event of an arc flash. And when I say it's an active system, I mean it's an intelligent system. It's relay-based. It's not passive. Like traditional arc-resistant equipment is essentially a robust enclosure that just sits there. There's no intelligence to it at all. It just sits there passively, and if it's all buttoned up, all the doors are closed, it works as designed. Arc Quenching Switchgear is an active and intelligent relay-based system, and it really has advanced the state of the art for arc flash protection, detection, and mitigation. So there's a little bit of an eye chart, this slide, but really the benefits of this technology really kind of just stem from this first bullet, and that is Arc Quenching Switchgear reacts 10 times faster than systems that rely on an opening a breaker to clear a fault. So virtually everything that we've been relying on for literally decades to clear a fault, to reduce incident energy, as Chris explained, rely on tripping that upstream breaker, a breaker that could, depending on the size of it, take 3 to 4 cycles to clear the fault. So energy reducing maintenance switches, zone selective interlocking, arc detection relays, bus diff, all those are kind of hamstrung by the speed of that breaker clearing. So what we did is we developed a system that operates a full order of magnitude faster than systems that rely on a power circuit breaker to clear the fault. And when you reduce your clearing time by an order of magnitude, you can reduce your incident energy by a full order of magnitude. And if you're reducing your incident energy by 10x, that may enable you to lower your PPE requirements. You may be able to decrease your arc flash hazard boundaries. We actually reduced the clearing time to such a low level that we were able to reduce the incident energy to such a low level that damage to the switchgear in the event of an arc flash is greatly reduced or completely eliminated. And that really gives you two main benefits. First, it minimizes downtime, because if you've got less equipment that needs repairs, or if there's no repairs needed after an arc flash, you're down for a much shorter period of time. But it also just protects what may be a $250,000 piece of switchgear or $500,000 piece of switchgear. So it just saves money by protecting that equipment itself from damage, and obviously keeps your processes, minimizes the downtime of whatever processes are being fed by that switchgear. Arc quenching switchgear reduces the incident energy to such a low level that the switchgear can actually pass that IEEE ANSI C37.20.7 arc resistant test guide in standard NEMA 1 construction. So that means the incident energy is so low that there's no longer a need for thicker gauge steel, 3-point latches, piano hinges, ducts, plenums, all that stuff that's required to make traditional passive arc resistant equipment arc resistant, essentially making a bomb-proof box to contain all that energy. It's no longer needed because there's such little energy emitted from the arc flash, because it's quenched so quickly that you don't need a robust enclosure to contain what little energy is released. And the incident energy is actually reduced to such a low level that the switchgear will exceed those arc resistant test requirements by passing the arc resistant test, even if a door is open or a breaker is removed. So typically when you perform an arc resistant test, C37.20.7, per that test guide, you place cotton indicators that are calibrated to burn at about 1.2 calories per centimeter squared. You place these cotton indicators 4 inches in front of the switchgear around all 4 sides. And then you intentionally ignite an arcing fold inside that equipment. And if one of those cotton indicators burns, it's a fail. That sort of represents one of us standing in front of the switchgear in just a cotton shirt, which obviously is a no-no under any circumstances. But that's sort of the idea behind the test. With our quenching switchgear, if you have a door open, those cotton indicators will still not burn. And that's pretty much unheard of. I mean, this really represents a quantum leap above traditional arc resistant equipment, which, as Chris explained, needs to be completely buttoned up in order to be able to contain that massive amount of energy that's released when there's an arc flash event. Our quenching switchgear is also an always-on system. So it's not like an energy-reducing maintenance switch where you need to train your people to turn it on when maintenance is being performed on the equipment or downstream of the equipment, and then remember to turn the system back off when maintenance is done. Otherwise, you may risk nuisance operation because the breakers are more sensitive. So, say a motor starting, so some large inrush current could potentially cause a nuisance operation. That is not a risk with our quenching switchgear. It's an always-on system. There is no switch to turn it on and off. It's always protecting the switchgear, and it has no effect on the coordination of the circuit breakers. It operates completely independently, and so you'd coordinate the system as you would even without the system, and it just sort of operates on a different plane and has no effect on the coordination of the breakers. Our quenching switchgear is also a current limiting system. So unlike, as Chris explained, crowbar or bolted fault systems, which are very high-speed systems for quenching arc flash, but when they operate, they apply a zero impedance fault, or practically zero impedance fault. So they draw peak fault current, which, as Chris explained, can damage your upstream power distribution equipment. This system actually introduces some impedance, so it reduces peak fault current by at least 25% when compared to a bolted fault or a crowbar system. And since electromechanical forces are related by the square of the current, it actually reduces the stress on the power distribution system when it operates by at least 44%. And I've seen the stress be reduced by as much as 60% compared to a bolted fault system. And of course, it's that stress that can damage the secondary windings on your transformer, tear cables out of the termination, cause cable whip, and that sort of thing. So it's really important to avoid applying a bolted fault to your system whenever possible. And this system does not do that. It reduces peak fault current when it operates. And it's got technology to avoid nuisance trips. So it will not nuisance operate if you have a feeder breaker in the switchgear that clears a downstream fault. As Chris explained, when a feeder breaker clears a downstream fault, a bunch of arc light will come out of the back of that circuit breaker. And that'll cause most arc detection systems to nuisance operate, because traditionally arc detection systems look for light and current. So when there's a downstream fault, there's high current, so the arc detection relay sort of checks that box, says, yep, hey, I got high current. Then the main contact's in the breaker part. A bunch of light comes out of the back of the circuit breaker. The relay says, oh, I also have light. I've got light and current. It must be an arc flash. And then it sends a trip signal to the upstream breaker, that main breaker, and takes the whole board offline. When really, you just wanted that feeder breaker to clear the downstream fault, whatever, maybe something going on in the MCC. So that's how a typical arc detection system would react. But we've developed technology that actually interlocks the operation of all the circuit breakers with the arc detection system so that you eliminate that risk of nuisance operation when you get that high current and light from a feeder breaker clearing a downstream fault. Talk just a couple quick specifications and then hit on exactly how the system works. But at a high level, as a sort of been implied by my previous comments, the system consists of two main parts. The brains of the system is the Eaton arc flash relay, which looks for flash of light from an arc flash and then uses that security signal of current, high current, just to validate that it is an arc flash and not just somebody with a bright flashlight or a sunbeam or something like that. So that's the brains of the system. So not a lot of innovation here. As Chris said, arc detection systems have been around for a long time. The real innovation here was just figuring out how to eliminate that risk of nuisance operation. So the arc flash relay is the brains of the system. Then the arc quenching device is the heart of the system. And this is what we spent the last 6 years actually developing is this arc quenching device. As you can see, it kind of looks like a draw out breaker. There are line side finger clusters. It's actually the same form factor as a Eaton Magnum DS breaker. So it can be withdrawn from the switchgear if it needs to be replaced or serviced. But internally, it has absolutely nothing in common with a circuit breaker, but it does fit in a circuit breaker cell. So the arc detection relay and the arc quenching device work in concert to provide that incident energy reduction that I described. So the system in Magnum switchgear has been tested to that arc resistant test guide. So it can pass the test guide in standard NEMA 1 construction, so no ducts, plenums, none of that reinforced enclosure. The arc quenching device is compliant with this brand new UL 2748 standard for arcing fault quenching equipment. So just a safety standard that UL has developed to govern these products. The switchgear itself has a short circuit withstand rating of 85 Ka at 635 volts and a short time withstand current rating of 30 cycles. And the entire system can operate and quench an arcing fault in less than 4 milliseconds. I'll go into a little bit more detail on how it does that in a couple slides. But that's what drives the incident energy down to extremely low levels, because 4 milliseconds is about a quarter of a cycle. So typically, with other incident energy reducing methods, we're talking a matter of cycles to actually clear a fault, not less than a cycle. So it's extremely fast. As I said, it reduces peak fault current, reduces system stress. Since it's an intelligent and active system, it's able to perform complete system self-supervision, so it's constantly monitoring its health and communicating that out. So if anything goes wrong, the end user will be notified. It's available in every switchgear configuration that Eaton makes. Traditional rear access, that is with the cable compartment in the back. Front access, where essentially we fold the cable compartment around to the front, so you've got a column of breakers, then a cable pull section next to it, then a column of breakers and a cable pull section. So it can be put against the wall, kind of like a switchboard, but maintains a UL 1558 rating. It's available in all enclosure types, so traditional indoor, NEMA 1, NEMA 3R outdoor, so it essentially creates the world's first outdoor arc resistant switchgear, because up until this point, NEMA 3R gear has not been tested to the arc resistant test guide. And it's even available in an arc resistant enclosure. If you were interested in sort of a belt and suspenders approach to arc resistance, active system, passive system, some redundancy there, it's also available in that. So how does the arc quenching system work? First, when there's an arc flash, light and current are detected by the arc flash relay. CTs are actually mounted on the line side of the main breaker, and then point sensors, wired point sensors, not fiber optic, wired point sensors that are strategically installed throughout the switchgear pick up that flash of light. So light and current, when both those signals are sensed by the relay, that relay sends out 2 trigger signals. The first one goes to the arc quenching device and tells it to operate. And the second one, which is sent out simultaneously, is sent to that upstream overcurrent protective device, that upstream main breaker, telling it to trip. Now, it takes less than 4 milliseconds between when the arc is detected and when the arc quenching device operates and commutates and contains all that arc energy. Then 3 to 4 cycles later, that upstream breaker trips and de-energizes the lineup. So obviously the question here is, how does the arc quenching device work? Light detection systems are, pretty well understood. So really kind of the interesting part here is actually what's happening inside that arc quenching device for that, in that very short period of time when it's told to activate by the arc detection relay. So that arc light is detected by the light sensors in the line side CTs. That relay sends the trigger signal to the arc quenching device. And then what the arc quenching device does is it creates a current limited, right? Not a bolted fault, not a crowbar. It introduces some impedance, a current limited, lower impedance arc. Essentially what it does is it creates a path of lower impedance, because current always follows the path of lowest impedance, event across all 3 phases located inside arc containment vessels. So that causes the arcing to instantly extinguish inside the switchgear, and all that arcing current, all that energy flows into the arc quenching device and is contained inside the arc quenching device, and there it continues to actually arc inside the arc quenching device until the upstream breaker opens up and de-energizes the lineup. So the arc quenching device works in the same concept as a crowbar device or bolted fault device, in that it creates a path of lower impedance for that energy to follow whenever there's an arc flash detected. The difference is that it actually introduces some impedance to reduce that peak fault current. So not only is protecting the switchgear itself, but it's also protecting the upstream equipment from dangerous electromechanical forces that can occur when you draw peak fault current. So I know that still doesn't really get to the meat of the issue here, and that is, how does the arc quenching device actually create that lower impedance fault? So this is probably my favorite thing to talk about here. This is what's inside the arc quenching device. There are actually 2 arc containment vessels. What's shown here are cutaways. They kind of look like vacuum bottles, VI bottles, but they're not. In the top of the left arc containment vessel, phase A is tied. And at the top of the right arc containment vessel, phase C is tied. And then phase B is tied into the bottom of both arc containment vessels. And these tan things shown here are contacts. If this were a bolted fault device or crowbar device, whenever an arcing fault's detected, triggering the device would mean just bringing these 2 sets of contacts together, just sort of clapping them together and creating a zero impedance fault that ties all 3 phases together. And that's actually kind of how a lot of arc quenching, or crowbar devices work. They essentially just tie all 3 phases together very quickly in a zero impedance. Essentially just tie all the conductors together very quickly and create that path of lower impedance, which quenches the arcing fault. But again, we didn't want to introduce a bolted fault to the system when there's an arc flash. So these contacts are actually fixed in place. This air gap does not change under any conditions. And you notice I said air gap. These arc containment vessels are actually filled with atmospheric air. They're not vacuum bottles. Because we actually want arcing to occur inside these arc containment vessels under certain circumstances. So under normal operating conditions, the contacts are far enough apart that there's no arcing across them. So 635 volt switchgear, no arcing across the contacts. You can even high-pod or dielectric test the switchgear with the arc quenching device, install that 2200 volt insulation test, and it will not cause it to fail. So under normal operation and normal testing conditions, there's no arcing across these contacts. But when an arc flash relay detects an arc flash inside the switchgear, it sends a trigger signal to the arc quenching device. And what happens when the arc quenching device receives that trigger signal is it dumps current into this blue wire. And what happens is this blue wire actually runs up the side of each of the lower contacts, across the top of each of the lower contacts, and then it doubles back on itself and returns to the trigger board. So when the arc quenching device activates, what happens is the trigger board dumps current into this wire, and that current flows through the wire. And what happens when current flows through a wire? Generates a B field, right? A magnetic field. Good old right-hand rule. So let's say current flowing from right to left across the contact. Let's use the right-hand rule. Let's say that is a counterclockwise magnetic force. Then that current comes and it flows back around, returns to the trigger board. Current flows in the opposite direction and then generates a clockwise magnetic force. So no matter about 200 microseconds, the arc quenching device has created two opposing electromagnets in this little wire. So what that does is it causes the top half of that wire to be repelled from the bottom half, and it jumps up and it jumps out of the way. But lo and behold, it can only jump so far and hits that top contact. And there it momentarily ties phase A to B and phase C to B. But that wire is so thin that it can't conduct full available fault current and voltage. So that copper wire melts, it vaporizes, and then it ionizes. And when you ionize copper, you have an arcing fault. So we've spontaneously created two fully contained arcing faults that tie all three phases together inside the arc containment vessels. So essentially what we've done is we've created a path of lower impedance for that arcing fault energy to flow so that it immediately extinguishes itself in that unintended location. It reignites as an arcing fault fully contained inside these arc containment vessels. There's no venting outside these arc containment vessels. That energy is fully contained. But since we used an arcing fault instead of a bolted fault to create this path of lower impedance, we've introduced some impedance so that it draws less peak fault current. Now, it may kind of seem like we're kind of walking a tightrope here. Like we want to create a path of lower impedance, but we want to add some impedance. So what if we add too much impedance and then it doesn't actually work? Well, that's a good question, and it does seem like it's a tightrope that we're walking, but it's actually not, thanks to the UL 1558 standard, which governs metal enclosed switchgear. And that standard says, among many other things, that the minimum distance between uninsulated power conductors in the switchgear is 1 inch. So that means inside UL 1558 switchgear, all of the power conductors that are uninsulated are 1 inch or greater apart. So by placing these two sets of contacts less than 1 inch apart, when we create an arc across them, we are guaranteed by the laws of physics that arc will be lower impedance, that current path will be lower impedance than any other possible current path in the switchgear, thanks to UL 1558 and that 1 inch minimum rule. Also, we know that arcing faults self-extinguish, believe it or not. If you create an arcing fault inside a piece of equipment and supply it with unlimited current and voltage, current and voltage for an unlimited period of time, those contacts will, that arcing fault will blow up, it'll blow the equipment apart, and soon enough those contacts will melt far enough apart that arc will self-extinguish. The equipment will be completely destroyed by then, but it will self-extinguish. So by containing the arcing fault inside these arc containment vessels and using special contact material that does not erode very quickly in the presence of an arcing fault, we ensure that the arc will not self-extinguish, that it'll continue to arc from A to B and B to C across these contacts, and it'll be fully contained. We won't let any of that energy escape into the environment and therefore potentially extinguish the arcing fault. So those two ways, we're sure that the arc quenching device will always be the path of lowest impedance when it's triggered by the arc detection relay. So the system's been designed to be super reliable. As I mentioned, it's got real-time health monitoring of all critical components and trip signal connections. So it provides dry contact health outputs, Modbus. There's a local indication on the equipment just a white light that's illuminated that says the system's healthy. As I mentioned, there's technology to eliminate the risk of nuisance trips, because the last thing you want to do is take your board offline if it wasn't a true arcing fault, if it's just sort of an accidental event. That's the last thing you want to do. The Arc Quenching device itself has redundant main control units. If one fails, the other one will pick up and it'll still operate. We've performed extensive reliability studies on all of the equipment. It's been actually tested and designed to the same standards that govern motor protection relays, transformer protection relays, that sort of thing. And it's actually shown to be just as reliable. We actually performed accelerated life testing on the device, and it's predicted to last, it's actually predicted to exceed our stated 30-year life of the switchgear. So for all intents and purposes, we'll just say the Arc Quenching system is designed to last the entire life of the switchgear, so 30 plus years. And the Arc Quenching device itself, as I said, is compliant to this brand new UL 2748 standard. So in terms of maintenance and testing on the system, we're not asking that you perform additional maintenance intervals, but whenever maintenance is performed on the switchgear, that's also, it could be a good time to do some testing on the Arc Quenching system. So whether you do that yearly, you maintain your switchgear, you do it every 3 years or every 5 years, depending on the kind of environment the switchgear is operating in, that also is a good time to test the system. The testing is really fairly simple, just involves plugging in the Arc Quenching system tester, which provides current injection to the relay, and it puts the Arc Quenching device into test mode, and then you can flash all of the point sensors with a provided high-powered laser. Again, we use a laser because it allows you to flash the sensors from a distance because it's so bright, you don't have to be right on top of them. And that verifies that the Arc Quenching device itself is operating. It'll non-destructively do a test fire to verify that everything's working. And then obviously when you flash all the sensors, it just verifies that they're all connected. Now, that being said, if a sensor does lose connectivity during normal operation of the switchgear, the relay will notify you. If the Arc Quenching device loses connection to the relay, or the trigger ribbons go bad, or the capacitor failure, anything goes wrong with the Arc Quenching device, you'll also be notified locally via LED light, remotely via Modbus. So the entire system monitors itself from end to end and will notify you of a problem, but it also, for peace of mind, can be tested from end to end. In terms of installation and footprint, what's required is one Arc Quenching device and one set of relays per main breaker. So if you have the main tie main lineup and the ties open, you're essentially operating two independent lineups potentially. So that's what drives that. You've got to be able to quench an arcing fault on bus A or bus B. Now, if you just have a single-ended lineup, one main breaker, you need one Arc Quenching device and one set of relays. They're installed in the same structure as the main breaker. They can be installed on the line on the load side of that main, and that is an important distinction. I don't have time to get into why that matters, but that is something that it warrants a further discussion when we have time. The point sensors that detect the arc flash light, there are 3 installed in the cable compartment of every structure, 2 installed in the bus compartment of every structure, and 1 over the finger clusters of every draw-out device. And those are tested and validated locations. These aren't just sort of our best guess. These are actually, we did arc flash testing on multiple pieces of switchgear to validate where the sensors had to be to ensure that they would be placed properly to detect an arcing fault no matter where one initiated inside the switchgear. And again, we use wired point sensors, not fragile fiber optic loops. There are a couple benefits to that. First, the wired point sensors can be installed in the factory, and so the system can be fully tested before the switchgear ships. Whereas typically, if fiber optic is being used as a light detection sensor, it needs to be installed in the field because it doesn't span shipping splits very well. So essentially, all the shipping splits of the switchgear need to be set down in the field. Everything needs to be cabled up, and then the fibers run. And that prevents the system from being fully tested at the factory. So again, that's why Eaton has chosen to use wired point sensors. Just improves the reliability of the system and ensures that it'll work as designed when it reaches the field. So in the event of an arc flash, another benefit of the wired point sensors is that they will indicate the location of where the fault occurred inside the switchgear. because the relay knows which sensor saw the light, so it'll be able to direct you to where in the switchgear that fault occurred. So personnel would go, they'd they'd locate and remove the cause of the event, they'd evaluate and clean the equipment. Arc detection system Arc quenching system operates so fast that it does protect the equipment from damage. It should still be inspected just to ensure that there was no damage. And if there is any minor damage, it should be repaired. So the equipment would be evaluated, it'd be returned to normal operating condition, and then the arc quenching device would be replaced. It's a one-time use device. We don't service them or repair them or refurbish them. They're removed, just drawn out of the switchgear, and a new one is put in service. Now, if a replacement device isn't available on the shelf, that's okay. The switchgear can still be re-energized with no device in the arc quenching device cell. But you just have to remember that the protection falls back to the speed of the relay tripping the main. So instead of a 4 millisecond arc quenching time, you fall back to anywhere from a 50 to 60 millisecond clearing time. So your PPE would temporarily be higher until you had a replacement arc quenching device installed. And the arc quenching device can be racked into to energized equipment if your safety procedures allow, and then bring the equipment back up to its fully protected state. So moral of the story is, equipment downtime is greatly reduced since repairs will be minimal and most likely completely unnecessary, and the arc quenching device is just simply replaced just as like a draw breaker would be swapped. So in terms of incident energy, I use the old IEEE 1584-2002 method here just for simplicity, and compared a number of different ways of clearing a fault at 480 volts and 85 kA available fault current. On the right-hand side, if the main breaker held in for a full 30 cycles, the incident energy would be nearly 90 calories per centimeter squared, and that is exactly what the equipment would look like. That is performing arc-resistant testing on non-arc-resistant gear and holding in that fault for a full 30 cycles. So definitely worst-case scenario, but the equipment's completely destroyed. Then on the other extreme is that same test performed on our quenching switchgear, 480 volts, 85 kA, a 30 cycle arcing fault, worst case. And this is a snapshot of that testing at that same moment in time. Pretty marked difference between NEMA 1, traditional NEMA 1 equipment, and arc quenching. I could show you a video of that testing, but it's kind of boring because nothing happens. This is the fun stuff to watch up here, as long as it's under test and not accidentally occurring. So I'm going to get rid of that breaker short time column just to get a little bit more granularity. So again, at 480 volts and 85 kA, zone selective interlocking comes in at about 12.3 calories per centimeter squared. Software instantaneous trip at about 10.2. Bus differential and arc detection relays. So just an arc detection relay just tripping a main, not tripping the arc quenching device, come in about 9.1. Eaton's energy reducing maintenance switch, which is called ARMS, comes in at 5.8. It's lower than an instantaneous because it actually uses a parallel analog trip circuit, so it's not relying on the electronics, the RMS voltage calculations and whatnot of the trip unit. It uses a parallel trip circuit, so it's actually significantly faster than instantaneous trip. That brings it down to a pretty respectable 5.8 calories per centimeter squared, but then our quenching switchgear comes in at 0.7. So well below that 1.2 calorie per centimeter squared threshold for which you'll get second degree burns if you're not wearing any PPE, which, you know, shame on you if you're not. But so 0.7, so again, an order of magnitude or 2 orders of magnitude lower than what has typically been available to us for reducing incident energy. So pretty dramatic reduction. And it's that extremely low incident energy that allows the switchgear to survive an arc flash event without being damaged, and allows it to be brought back online much faster to get those critical processes running again. Now, obviously, our quenching switchgear can be modeled pretty trivially in EasyPower. You would just plug in a clearing time of 4 milliseconds, and the software will do the rest. If you have any specific EasyPower related questions, please contact their technical support. They'd be happy to walk you through how to model our quenching switchgear in EasyPower, but it can be done very efficiently and easily in the EasyPower software. So, in conclusion, Arc Quenching Switchgear really just does one thing, and that is it reduces incident energy. But it just does it to an extremely low level. And it's able to reduce incident energy to far lower than virtually anything else there. And that's where all the other benefits come out. But it's really just an incident energy reducing technology that enhances safety and enables standard switchgear to exceed that arc resistant test requirement even when doors are open. It provides advanced equipment protection when there's an arc flash. And as a result of not having to do many or any repairs to the equipment after an arc flash, it dramatically reduces the downtime so that you can have your critical processes back up and running very quickly. So that's all that Chris and I had. We really appreciate your time. I think we can take questions. Maybe Jim can clarify how we want to do questions, but I think they can be typed into the chat window, or you can email me directly, and I'll get back to you as quickly as I can. And we've got a bunch more information on the web.
Adams, that was a great job. Thank you very much. It looks like Chris is handling most of the questions as they've come in. So I wanted to thank both of you for your participation, and we will be posting the webinar on the EasyPower website within the next week and a half. We'll leave the session open for another couple minutes in case you have questions that you want to enter that we can answer via email. But again, we'd like to thank Eaton Corporation very much for their support. Have a good day.